Have you ever wondered how we can simply solving complex problems like network optimization or scheduling? These are challenges that often seem impossible to tackle because of their complexity. That's where decomposition comes in, a powerful method that helps break down these tough, NP-hard problems into smaller, easier to solve parts. In this video, we will take you on a journey to understand what tree decomposition is, why it is important, and how it is used in areas like graph coloring and network analysis. Each team member will dive into a key aspect of the topic to give you a full picture. Let's begin.
Let's talk about some problems in graph. One of the problems we have in graph is graph coloring. I know you might be thinking, what is graph coloring? Graph coloring is a process of assigning colors to the vertices of a graph so that no two connected vertices with an edge between them share the same color. So imagine you're scheduling exams with different subjects and each subject is a vertex. And if two subjects have common students, they are connected. So now you're in the challenge. The challenge is to use a few time slots or colors as possible. Another problem we have in graph is the vectors cover problem. So the vectors cover problem is where we need to pick the smallest number of points to cover all connections, which is the edges. An example is choosing the minimum number of cars to watch over a network. How does the traditional approach struggle with a large graph? So when the graph gets very big, like a social media network with millions of users, solving this problem becomes very slow and uses too much memory. This is where tree decomposition comes to the rescue. Tree decomposition breaks the big graph into smaller, easier pieces arranged like a tree. So solving problems on these smaller pieces is much faster and simpler.
What is tree width? Tree width is a measure of how closely a graph resembles a tree, which is one of the simplest types of graphs. A graph's tree width is derived from is tree decomposition, a way of representing the graph as a tree-like structure that groups its vertices into overlapping subsets called bags. The smaller the tree width, the closer the graph is to being a tree. So what are some of the importance of tree width in efficient problem solving? Bounded tree width is crucial for solving computational hard problems efficiently in graph theory and discrete mathematics. Many problems such as graph coloring benefit from the structured nature of tree decomposition. Graph coloring with the tree decomposition can be further explained that graph coloring involves assigning colors to vertices such that adjacent vertices have different colors. This is computational hard for general graphs, but with the bounded tree widths, we can solve it efficiently. Using the tree decomposition, the graph is processed bag by bag. Dynamic programming ensures that coloring decisions in one bag are consistent with its neighbors in the tree decomposition.
So, we've already looked at tree decomposition and tree widths. But now, let us look at the types of problem that tree decomposition solves. So these are classified into domination, coloring, and routing problems. So these problems can affect efficiency in terms of communication, networking, and fast processing systems. Now, a graph with a larger tree width has a more complex structure compared to a graph with a smaller tree width. So let us look at some examples of graph coloring algorithms which are used to solve graph coloring problems. So one includes the first fit coloring, which assigns each vertex the smallest possible integer that is not already used by a neighbor. Another example of graph algorithm is the K1 coloring algorithm, which aims to use a few colors as possible while ensuring that each node's neighbors have a different color.
Tree decomposition is not just a theory. It helps solve real problems in different fields. In data management, it speeds up data queries. Instead of searching everything at once, tree decomposition organizes data in a way that retrieval is faster and easier. In bioinformatics, it helps analyze protein interactions. By breaking networks into smaller parts, scientists can better understand how proteins work together. In our research, we also saw how tree decomposition helps with network traffic optimization. It makes routing in AI-driven networks more efficient, ensuring quick and reliable communication. Tree decomposition, therefore, connects complex problems to practical solutions in areas like database, science, and networking.
Now let's move on to advanced algorithms for 3D composition. Now that we understand why 3D composition is valuable, let's look at how to find it. There are several approaches. First, we have the naive approaches, which try all possible ways to decompose a graph. These methods are accurate but very slow, especially for large graphs. Next, we have the heuristic method, which use smart strategies to make this process faster while sacrificing a bit of accuracy. One popular method is the elimination order method, where we remove vertices in a specific order and create tree-like structure based on those removals. This method balances efficiency and accuracy. Now we'll go to trade-off. When choosing a method, we always face a trade-off. Do we want higher accuracy with a perfect decomposition, or we are okay with a faster but approximate result? For example, in real-time systems, speed might be more important than perfect accuracy. Understanding this trade-off is key to applying tree decomposition effectively.
Now we'll be looking at the challenges faced in tree decomposition. Tree decomposition faces challenges such as inefficiency in dynamic programming when applied to large graphs with numerous vertices or edges. Finding an optimal tree decomposition is an NP-hard problem, meaning it is computationally infeasible for complex graphs. Suboptimal decomposition with larger tree widths can increase the complexity of graph coloring algorithms, reducing their practical benefits. To address these challenges, heuristics like greedy algorithms are used to find approximations that are efficient, though slightly less precise. Tools like the Network X and TreeWidthLib help simplify implementation by providing ready-made algorithms for decomposition and graph problem solving. Additionally, parallel and distributed computing techniques enhance the scalability of these methods, enabling the processing of larger graphs in less times.
We'll be talking about caudality. According to Boyd Landon Lewis, in his article titled Tree Width, Algorithm Techniques and Results, a graph is caudal if and only if each cycle of length of at least 4 has a chord. So a chord is an edge between two vertices that are not successive on the cycle. Now let us look at the relation between caudality, tree decomposition, and tree width. So every caudal graph has a tree decomposition where each bag corresponds to a maximal clique of the graph. Conversely, if a graph has a tree decomposition where the bags form cliques, the graph is caudal. Tree width and caudality. Computing the tree width of a graph is NP-hard in general, but caudal graphs make the process easier, since their tree width corresponds to due size, or to the size of the largest clique minus 1. So let us look at graph minus. A graph minor is a graph that can be obtained from another by either deleting the edges, vertices, or contracting the edges, which means merging two adjacent vertices into one, combining their incident edges. So some of the key properties of graph minors is that minors are more general than subgraphs because edge contractions are allowed. Also, the concept of minors is used to define and study graph invariance, properties preserved under minor operations. Let us now look at structural theorems. So these provide the frameworks to describe such classes. So let us look at tree width and minus. So the tree width is closely related to graph minus. And also the algorithmic implications. So the minor relationship and structural theorems allow the design of efficient algorithms.
Tree decomposition is a powerful tool in AI and machine learning, especially graphical models like Bayesian networks. It also plays a key role in message passing algorithms, which are crucial for making quick decisions in distributed systems. Our research shows that tree decomposition bridges the gap between AI-driven problem solving and real-world applications, making things like network routing and scheduling more reliable and efficient. Our research also demonstrates that there are still many open questions. For example, how can we improve the speed and efficiency of tree decomposition algorithms for larger graphs? What challenges remain in making tree decomposition work seamlessly in real-world data? We see potential applications of tree decomposition in new fields like quantum computing, where it can optimize data processing, and network resilience, where it helps in creating more stable and fault-tolerant systems. As researchers and problem solvers, you have the chance to explore these questions further. Remember that the future of tree decomposition is in your hand, and your innovations could shape how we tackle complex problems in AI. As part of our video agenda, we are going to solve problems and find use cases for you to understand and learn how to go about tree decomposition.